All right, next up we have Wolfpack Machina, team 18438. Wolfpack is a third-year FTC team from the Waring School in Beverly, Massachusetts. They've had the highest OPR and won the Inspire Award at the 2023 World Championships. Wolfpack was also the Software Award winner and Winning Alliance captain at the 2023 MCI. Wolfpack will represent the US and Singapore at first global with their sister team, Team 18224 Lupine Robotics. Sadly, Wolfpack was not able to, their software person was not able to host this session because of network connections, but they have recorded a full video for us. Give it up for Wolfpack.
Alright, hi everyone and welcome to Effective Vision Usage. This is just a short overview of some of the kind of tips and tricks that we've used to optimize our vision algorithms over the years. We've used vision in a lot of different seasons. We used it a lot in Ultimate Goal for auto-aiming towards that high goal with our shooter, and we used it a ton in this previous power play season for aiming towards the poles in auto and giving ourselves a lot wider margin of error. So, algorithms. Generally, the way that Easy Open CV, which is what FTC pretty much universally uses, is that you have these vision pipelines that process each image. You can essentially set a camera to run a pipeline. Most pipelines will go through the same, at least initial steps, where you will convert the color space from RGB to whatever color space you want to use. You'll then blur the image. You'll threshold the image, so you're essentially looking for pixel values in between certain thresholds of RGB or HSV or some color value. You will then erode and dilate that thresholded image to give you a slightly cleaner result, and kind of if there's a few pixels that are just kind of noise in the image, it'll get rid of those, and then you kind of expand out your detections back again to get to a rough approximate size of your true detection. And then finally, you normally find your contours. This is kind of blob detection where, going back to this opening image, you can see here we're thresholding for this blue, and then we're drawing bounding boxes around this blue by finding the kind of contour of the outside of this. So, to give you a quick overview of kind of what a full, complete, competition-ready system might look like, this is the very low-res, which we will talk about later, version of our Power Play auto-aim. So you're seeing here that it's detecting this pole, it's putting this little blue aiming reticle on it, and it's then moving our entire arm right to aim at that junction. So now, if I So the issues that we've had in the past with this are erroneous detections. We've been kind of detecting things that are behind what we're looking for that aren't the object that we're looking for. We've had changing lighting conditions. This is a big issue for a lot of teams that try to use vision. If you are using vision in different lighting scenarios across different competitions, that can lead to a lot of issues with trying to actually find the right target. Speed, frames per second of vision, I'll talk about this a little bit more and why I think it's really important. Noise in the data that you're gathering from vision, effectively using the data you get, and so kind of we've had a lot of vision pipelines, and I've seen a lot of people who I've mentored on other teams do vision pipelines that don't get the data as effectively as they could. They might be looking for something and then just kind of turning the robot like left if the thing is left, or right if the detection is to their right, if they're trying to like aim towards something. And a point I want to make here is that you can get a lot more data out of an image. A camera is really like a angular matrix color sensor. You can get a ton of data out of it. And that includes getting data on specific angle and range and everything to a target if you're using it in the right way. And so that means you don't have to, turn left or right slowly so you don't overshoot. You can just turn a set amount of degrees as fast as your, PID control loop will update. And then finally, buggy software, slow software. In software development and in software craftsmanship, there's this concept of badly behaved and well-behaved code. And the idea is kind of, are you using a library like it is intended and supposed to be used? And so it doesn't necessarily mean good code, bad code, but what I will caution in FTC is that I always recommend writing well-behaved code for Easy OpenCV. Write code the way that Easy OpenCV wants you to. Use Easy OpenCV. I've seen a few teams try to do kind of custom vision where like they use Easy OpenCV just to get the camera matrix and then they do all their own processing. The thing is that vision is one of the most computationally expensive tasks you are likely to be doing on your robot. In fact, if we're adding likely to be doing, it is the most expensive computational task you're likely to be doing on your robot. And so using Easy OpenCV is going to be optimizing that way more than you are ever going to reach from within the FTC SDK. Getting better detections. In Ultimate Goal, we had a robot that aimed at the goals. I was our human player that year, and I had to wear a different shirt than the rest of my teammates because I couldn't wear the pink shirts we normally wore because the auto-aim would aim at it. So we had a lot of issues with stuff in the background. We had a match at MTI that year that got messed up by the fact that there was a roll of tape on the table in the background. The kind of quickest fix to this that we actually really implemented this year is just to not use sideways facing cameras. If you can put a camera on the top of your robot and face it down, kind of the less area you're seeing and the more of just the field you're seeing, the better, because you know what's on the field. You know what the field tiles are going to look like. The only really thing you might not know is exactly what other robots look like, but you don't need to deal with the background wall at the tournament we're at is the exact same color as the object we're trying to aim at. So I always recommend, when possible, downwards facing cameras. Or something like April tags. April tags are nice because they're deliberately designed to kind of not get confused with background noise. You're really unlikely to get a false detection, and also because you can get size and distance information, even if, let's say, you're seeing an April tag on, the next field over, if it's a 2-field event, you can still threshold for that. You can say that we only want to detect April tags that are less than 10 feet or 12 feet away or whatever, right? Thinking about what data you want and need out of your vision pipeline. So for instance, what we were trying to get is the top point on the cone pole. And so to get the top point on the junction pole, we were detecting this yellow of the junction. We couldn't really detect the black on the top because it was too similar to the field tiles. And if we tuned it for our room, yes, we could detect it, but we didn't feel confident that if we tuned it to detect that in our space and then went to a tournament where the lighting was different, that we weren't going to get bad detections, because that kind of like slightly reflective black is just way too common a color. So we were detecting the yellow on that junction, which we could really precisely threshold for. And what we did is we basically drew a line from the center of our image through the center of our bounding rectangle, and then found its exit point on the bounding rectangle. Initially, we were just using a corner of the bounding rectangle, but then the issue that we started having even more was that if it was like right on a vertical or horizontal, it would kind of be like alternating back and forth, and because the box had a width, it would lead to really noisy data, and it was really bad. So design your vision pipeline around trying to figure out what information do you want out of it. Be prepared to tune and calibrate. This is something that really helped us at our first MTI have working auto-aim when a lot of other teams were having issues with their auto-aim, is we didn't just threshold for our room, we assumed that we were going to have to calibrate. All of our vision parameters were in FTC dashboard, and we even had a calibration sequence, like a op mode, that we just turned on, aimed our robot at the goal, pressed a button, and it would actually save that calibration to the control hub, or even just output values that we could then manually type in. The other thing that's really important is choosing the right color space. Never use RGB. Never use RGB. The reasons you should never use RGB are that it's all relative. A color that has like a lot of red, if you're looking for something that's red, right, this has 255 red, but like this white over here also has 255 red. This red, this purple, it's kind of hard to threshold for these like triangular sections in color space with RGB. And so a color with like this value you also think is red, but the red value is kind of low. A color over here, same red value as this that looks very obviously red, is like very green. So RGB is a really terrible color space to try and threshold in. I don't recommend you ever subject yourself to trying to threshold in RGB. What we more often use is sometimes YCRCB, which can be nice for some things, but most often, and the one that I like the most, is HSV. HSV has a color space where the hue is represented as an angle, the saturation is kind of this like radius, and the value is kind of this up-down of this cylinder. Saturation, how white, how washed out is it, value, how black, how dark is it, and then hue is just an angular measure. The one issue with HSV I have seen talked about, and I've seen teams have issues with, is where they want to detect red. And the issue is that red is on kind of both sides of HSV. There are OpenCV color things that like kind of fix this. You could do some complicated like angle wrapping program for thresholding, but the basic issue is that if you set a threshold here, you either have to have another threshold statement to catch this bit of red over here, or some really complex thing to wrap this around. You can also do a method that is actually officially suggested by the OpenCV forums and seems a little bit cheating, but works really well, and that is that blue is really easy to threshold. It's right in the middle here, it's really easy to find. And so rather than converting from RGB to HSV, just convert from BGR to HSV. Just swap the color channels. That is what we did during power play, is our color channels were just swapped, and so this is not exactly what it looks like because I just inverted the image because I didn't have the proper color editing tools on me, but basically that kind of puts red right in the center of this because you're literally just swapping what it interprets as red and blue. So that's a really easy way to threshold for red. It's also nice because in FTC, you have red alliances and blue alliances, and often it means you can use similar thresholds and you're working with similar values. And so if you need to like swap pipelines or tune up, sometimes you can use actually the same thresholds for both your blue and red pipeline. More on fixing bad detections, masking. In Ultimate Goal, we had a horizon line so that we weren't, seeing these, we weren't seeing any of the stuff on the field. We were only detecting stuff above a certain limit. And then for power play, because the cone was red and could sometimes get confused with darker parts of the junction pole, because kind of a dark yellow will actually read in HSV or with a slightly noisy camera sometimes as red. To fix these kind of detections, what we would do is we would have this kind of circular mask here. That's this white circle you're seeing. It's actually pretty simple to do this in OpenCV. You generate a mask matrix that you just fill with zeros initially. You draw a circle in that that's like just filled in, and then you do a bitwise and. So you're literally just saying, is this pixel and this pixel both white? And because your mask is all white, and then the rest of it is all black, then anything beneath that white section is going to make it through, anything that isn't. And so that's a really great way to be able to do these kind of like any shape you want, because we were actually looking through the cones towards the poles. Other optimizations, speeding up the camera. I see a lot of people just code their vision pipeline with the default resolution and just leave it that way. I highly encourage you to look at different resolutions. A lot of cameras support tons of different resolutions, actually. They have like really wide angle ones that are that will give you like a whole like 1920 by 1080 if the camera's like a full HD webcam, right? You might be able to get a strip of 1080 pixels by like 40 pixels or something. And so it's a low-res image by absolute pixel count, but if you're like just scanning and that's all you need, you're maybe looking for poles on a field or something, like if you were aiming horizontally out in power play, then you might only need that kind of strip of the image, and then you're not running vision processing on all the rest of it and using up all of those computer resources and making your vision pipeline run slower. Using lower resolutions often is fine. We used a really low resolution in power play, like 144 by something, just because we didn't really need anything else. The movement of our arm, the trigonometry behind that, the conversion of the camera, everything was less accurate than 144 by whatever pixels it was. That wasn't going to be our kind of our bottleneck, our limiting factor on the accuracy of this system. And so we just went with as low a resolution as we could get without it being a limiting factor, and that meant that it could update a lot faster and give us more feedback data for any like denoising algorithms. You'll see I have that listed down here, denoising and signals analysis. Running like a low-pass filter or a rolling average or something like that helps you generally with sensors, but I also recommend people apply it to vision because cameras are kind of noisy things, especially if you're dealing with like somewhat low light or anything, or just weird lighting in general. Averaging stuff over multiple loops just generally gets you much better data. Back to my point about like cameras give you a lot of data. This is what our power play general imaging looked like essentially, is we were converting the pixel values to angle values using the known FOV of the camera. We didn't really have to worry about distortion because we were only really looking at the center part of the image. If you were doing this for a different game, you might want to look at some of the camera calibration functions of OpenCV. We were converting it to an angle, and then because we knew the height of our camera above the pole we were looking at, and we knew the angle of our camera, we could basically just do a bunch of trigonometry in 3D to figure out our X and Y distance. So if you have a single point and you know a plane that that point is on, if you have 2 points and you know where those are, you can get a full like 3D data out of that image. And then we fed that into our inverse kinematics algorithm that was basically just solved out as a system of equations that let us actually move our whole arm to a very specific point that we'd found this way. And so we didn't have to run like a PID that would, slowly pan across, aim, and then slowly go forward until it was in the right place. We could just take 1 or 2 scans with the camera and just move there. And that made it really fast. So I think that's it for kind of our general list of optimizations. And I'm a big proponent of vision usage in FTC. I think it's really useful. I think adding April tags in this upcoming center stage season is going to be awesome and gives a ton of opportunities for using vision for navigation. And I'm sorry I couldn't really do this talk live, and please reach out to me with any questions you have.